These are examples for section 9.4, similar right triangles. We're starting with example 2. Example 1 and practice 1 were covered in the notes. Example 2, correctly identify the similar triangles in the diagram right here by labeling each separately drawn triangle below. These three here. Notice how each right triangle has been transformed in each case. Then write a similarity statement using the three triangles. You learned in the lesson that when you have a right triangle and an altitude is drawn from the right angle to the opposite side, the hypotenuse, it creates two more similar right triangles. So we have three similar right triangles. The challenge many times can be trying to find out what corresponds to what, the vertices, the sides. And so a lot of times if you can come up with a little system on naming, it helps. So what I'm going to do is I'm going to start with the shortest leg, take a look at the largest right triangle, STR here, and kind of ignore the altitude for a moment. ST is the shortest leg and TR is the longer leg. And then RS is the hypotenuse. So if I start with naming the short leg, then the long leg, and then finally finishing it out with a hypotenuse, it's a system I can use when I name the other two right triangles. So starting with the largest right triangle, I'm going to start right here as I mentioned. ST is the shortest leg, TR is the longer leg, RS is the hypotenuse. So we have triangle STR, and down here would be STR. Is similar to the medium-sized triangle right here. Starting with the shorter leg, going to the right angle, we have TU, long leg, over to R, and hypotenuse is down here on the bottom. So triangle TUR is similar to triangle. Now for the smallest right triangle, we have, starting with the short leg, SU, and then the long leg, UT, and then the hypotenuse, TS. So SUT, SUT. So in this diagram, the triangle STR is similar to triangle TUR, which is similar to triangle SUT. Practice 2. Correctly identify the similar right triangles in the diagram at the right, this one right here, by drawing the remainder of the triangles and labeling each triangle separately. Then write a similarity statement. Pause the video, try the problem, and when you're ready, turn it back on. Practice 2. The largest right triangle is triangle DEF. I'm going to use the same system I used on the first one, short leg, long leg, hypotenuse. So we have DEF, triangle DEF, is similar to triangle. Now for the middle sized triangle right here, it's been turned over or rotated and flipped. And so the hypotenuse is down here. Here's the right angle. Short leg, start here with E, EG, long leg GF, and hypotenuse FE. So we have triangle EGF. So finishing out this triangle, we draw the short leg and the long leg. And so again, this is triangle EGF. Then the smallest right triangle, right here, starting with the shortest leg, DG, and the long leg, GE, and then back over on the hypotenuse, ED. So we have triangle DGE, similar to triangle DGE. So over here, finishing this out, we have DGE. Example 3, swimming pool. The diagram at the right, actually it's below it, shows a cross-section of a swimming pool. What is the maximum depth of the swimming pool? Well, first of all, before we talk about the depth of the swimming pool, let's look at the word cross-section. We're going to cover what a cross-section is in much more detail later in the units this semester. But just so you'll know, a cross-section is a two-dimensional figure or view of a three-dimensional figure that has been sliced or cut. So the swimming pool, if you could cut through the earth right in the middle of the swimming pool and look straight on, that would be called a cross-section of the swimming pool being a 3D object or solid. And so they want us to find the maximum depth. Well, the depth, of course, is from the top of the pool all the way down to its lowest point. Well, we've already got 48 inches from here to here, so we can't forget that. We're going to end up adding that to whatever we find right here, h, the height there. So we know we're going to add that. They've allowed us, or given us, tried to help us with these three triangles. So I'm going to go ahead and finish out the smallest right triangle here. Shortest leg and hypotenuse. And then I'm going to go through, let's go through and take a look at and see where all these vertices are. Taking a look at the largest right triangle with S, T, and R here. Starting with the shortest leg, S, T, then T, R, the long leg, and then R, S, the hypotenuse. So it's been brought over here, just slightly rotated, and we have S, and we have T over here, and R over here. For the medium-sized triangle, this one right here, this one has been flipped and then rotated slightly. Right now, the longest leg is at the top, hypotenuse at the bottom. Over here, the hypotenuse is at the top, and the long leg is at the bottom, so it's been sort of flipped there. So M is the right angle. I'm going to start with the shortest leg. So I have TM, and then over here to R. So triangle TMR is similar to triangle STR. And then our smallest triangle, our smallest right triangle, starting with the same naming system. I'm going to start at the shortest leg. So SM, shortest leg, MT, longest leg, and then back over to S, the hypotenuse. So SMT, SMT. At this point, what we can do, since we're trying to find the height of this, it's obviously a side of two of the triangles. And so we're going to put all the dimensions on here and see what we have, so we can use a proportion to find the length, or that h, the height of that distance there. So starting with the largest triangle, I have ST, which is 64. The longest leg would be RT, which is 152. The hypotenuse that runs along here is 165 inches. So we have all three here. That means we can use this triangle in our proportion no matter what. The middle-sized triangle, we have this triangle right here, and TR, the hypotenuse, is this time 152. The short leg is H, TM, and the long leg, MR, is, we don't know, 165 minus SMs, and we don't know what that is, so we'll leave that blank. Then for the smallest right triangle, we have the hypotenuse of it is 64, so TS is 64. The short leg, we do not know what it is. We know the whole hypotenuse of the big one is 165, but we don't know what that is, so we're going to leave that. And then the long leg is also H. So, we know we're going to use this triangle, the medium or smallest triangle. That's the one we need to determine which one we're going to use. It turns out in this problem we could use either one. So I'm going to start with the largest triangle and create ratios out of all the corresponding sides, with largest to either smallest or medium sized. It doesn't really matter which one I use. I'm going to go ahead and use the smallest one. Just make sure that you have corresponding sides and enough information. So if we use the mid-sized triangle, we could use the two hypotenuses and create a ratio. And then we could use the two short legs and we'd have enough information to find H. But it's also true over here. If we use the hypotenuse of the small and the largest, we have numbers for both. And then the long leg, and the long leg here, we have H. So I'm going to go ahead and use the smallest one. So this is how I'm going to set up my proportion and my ratios. So I'm going to start with the largest over here. I guess I'll start with the short leg. ST is to SM, as then the long leg, RT, is to the long leg here, TM, as the hypotenuse, RS, is to the hypotenuse over here, TS. Then if we go ahead and substitute in those values that we know, let's see what we have. We have ST, which is 64, is to SM, which we don't know, as then RT, which is 152, is to TM, which is H, as RS, hypotenuse, 165, is to the hypotenuse over here, TS, which is 64. Now if you take a look at these three ratios, one of them we are not going to use. It's this one right here, because we need H, and then we need another ratio with both terms as numbers. So we're going to use these two. By cross multiplying, we get 165H equals 152 times 64 is 9,728. Then solving this equation for H, dividing both sides by 165, we get H is approximately equal to 59.9576 and so forth. Let's go ahead and round to the nearest inch, or nearest tenth of an inch. If we round to the nearest tenth of an inch, we look at this is the place we're rounding to. We need this is 5. Since it's 5 or greater, it's going to push this up to 10. So there's the 0 and the 10. The 1 gets added to the previous place, which is the 1's place. 10 plus 1 is 10. We carry the 1 over here. 5 plus 1 is 6. So in other words, we get 60.0 inches. If we're rounding to the nearest tenth, we do have to have a tenths placeholder, even if it's 0. Don't forget, we were going to add the 48. This right here represents the height from here to here. So this is 60.0 inches. This is 48 inches. We need to add those using segment addition. So by segment addition, 60.0 inches plus 48 inches gives us 108 inches. Now if we find this in feet, we can take 108 inches and multiply it with a conversion factor. Remember, there's 12 inches in a foot. Now I can either put 12 inches up here and 1 foot down here, or 1 foot up here and 12 inches down here. To determine what goes where, I look at these units right here. I want these to go away because I want feet. So I need my inches down here in the denominator so that when I multiply the conversion factor, these divide or cancel out. Like that. So that means feet has to be up here. And so I have 12 inches for every 1 foot. So I'm going to use 1 foot over 12 inches. And then when I multiply these, I get 108, the inches divided out, times 1 foot, gives us 108 feet, over 1 times 12 is 12. 108 divided by 12 is 9, and then we still have feet. So this pool, its maximum depth is 9 feet. Example 4. Identify the similar right triangles in the diagram. Then find the value of x. This will be the first time we will identify the 3 right triangles created by a right triangle and an altitude without drawing or redrawing the triangles in a position that makes it easier to see. So I'm still going to use short leg, long leg, hypotenuse kind of system or pattern to name these, but instead of drawing the triangles out, I'm going to just use this diagram to do it. So here we go. I'm going to start. I'm going to put it right down here. So we have triangle. I'm going to take the largest triangle, which is triangle EGF, and there's the short leg, the long leg, hypotenuse FE. So EGF is similar to triangle. Now for the medium-sized triangle, which is this one right here, I'm going to name it by the short leg, long leg, and hypotenuse. That's GHF. Is similar to triangle, the smallest right triangle, which is right here. Again, taking the short leg, then the long leg, and then the hypotenuse, I have triangle EHG. Now, not only is this one of my answers, it can aid or help me in setting up proportions. Instead of using the diagram, I can use these vertices in the order they're in here. So to find the value of x, if we can set up a proportion using the fact that similar triangles have proportional corresponding side lengths, we can go ahead and see which two triangles we'd like to use. So if you take a look at these, looks like we have the three triangles. Notice that we've got the longest, we've got the hypotenuse of the largest one, and we've got both its legs. So it's a good idea to use the largest one because we have all three sides. So I'm going to start with the largest triangle and create a ratio either with the smallest or with the medium-sized triangle. To determine which one, both of them involve x because both of them have a side involving that x. The small right triangle, it has the long leg as x, and the medium-sized triangle has the short leg with x. So it doesn't really matter which one we use as long as we have two other measurements in both triangles, which we do. We have the hypotenuse here in the mid-sized triangle. We have the hypotenuse here in the smallest triangle. So it doesn't really matter which one we use. I'm going to use the largest to the smallest triangle. You could have used the medium-sized one. So if I set up proportion, I'm going to use the vertice names first. I'm going to start with, and I'm going to use these two here. Since I'm not using the middle one, I'm just going to cross through it. I'm going to start off with EG is to EH as GF is to HG as, and then finally EF is to EG. I did this whole thing without looking here. Just make sure this is correct if you use this method. Okay, now I'm going to substitute in values for all of these lengths. EG is 3, is to EH, which is, we don't know. EH is right here. So EH, I'm just going to leave like that. Probably will not be using this ratio. GF, which is 4, to HG, which is X, as EF, which is 5, to EG, which is 3. So obviously this ratio we're not using. We're going to use these two, cross multiply, and find how long GH is, the value of X. So when we cross multiply, we get 5 times X, or 5X, equal 4 times 3 is 12. Dividing both sides by 5, X is going to equal 2, and 4/10, or 2.4. So the length of this altitude for the large right triangle is 2.4 units. Example 5. Find the value of y. Write your answer in simplified radical form. So that means if we get a square root, we're going to simplify the square root. We're not going to approximate it. So here we have what looks like a lot like the previous example. We've got a right triangle with an altitude drawn from its right angle, creating two other similar right triangles. And it can be very helpful if we can look at those triangles and how they correspond to each other. So I'm going to go ahead, even though it didn't tell us to, I'm going to go ahead and write a similarity statement. Starting with the largest one, using my system of short leg, long leg, and hypotenuse, I've got triangle RQP is similar to the medium-sized triangle, which is right here. Short leg, long leg, hypotenuse. We have QSP is similar to triangle, the smallest right triangle, using that same naming system, RSQ. Okay, then I need to decide, since I'm looking for y, y is a part of the smallest right triangle. Y has nothing to do with the medium-sized right triangle, and in fact, the medium-sized triangle doesn't have any length given to us. It doesn't have QP, doesn't have QS, and it doesn't have QP, although we could find it. So I'm going to use the smallest and the largest right triangle here. So I'm going to get rid of that one. Now I'm going to set up a proportion very similar to the way I did example 4. Starting, I'm going to use the smallest this time, smallest triangle, to the largest triangle. You could do it the other way around if you wished. So here we go. Smallest right triangle. I'm going to start with the shortest leg. That would be RS is to the shortest leg of the largest one, which would be RQ. And notice it's harder to use the diagram. It's easier just to come down here and use this. So again, we had RS is to RQ. As back over to the small one, SQ is to QP. As, and then finally, RP, well, the small one first, RQ is to RP. RQ is to RP. Notice I corrected myself. I was about to use the large one first. The smallest one we decided was going to be on the top. So, alright, so now substitute in values for everything that I know. So RS here is 3, is to RQ, which is Y, equals SQ, which we don't know, is to QP, which we also don't know, as RQ, which is Y, is to RP. RP is the 9 here. Well, we're obviously not going to use this one. We have no information about it. So we bring these together. We have 3 is to Y is to 9. This is a classic example of the geometric mean. Back when we learned that these are the means, these are the extremes, when the means are missing, they're the same, then we can find through the extremes what the means are. So what we do is we still cross multiply. Cross multiply this way, that's Y times Y. Cross multiply this way, that's 3 times 9, so we get Y times Y is Y squared, equals 3 times 9 is 27. To get rid of the square, we take the inverse operation, which is to take the square root. We take the square root of both sides to balance the equation. Those undo each other, and so Y is equal to the square root of 27. Now, instead of reaching for a calculator, since we want simplified radical form, we're going to simplify this. Find factors of 27, and a factor of 27 that's a perfect square besides 1. We have 1 times 27, which we're not going to use, 3 times 9. 9 is a perfect square, so we split this up into, or factor it up into 9 times 3. Then we can split the square root. We have Y equal the square root of 9 times the square root of 3. And so Y, the square root of 9, is 3, and the square root of 3 will not simplify, so we get 3 times the square root of 3, and Y is 3 root 3 in length.